Hello, everybody. I am Manuel. But people usually call me Ling, so call me Manuel or Ling, whatever you prefer. Let's talk about the new regex library in Mojo. So yeah, we are going to start it with an introduction and explaining the why we build the library. Then a little bit of overview in the architecture because it's much more complex than I expected when I started the project. Then we are going to walk through the performance optimization. Uh, and yeah, the final is the roadmap for the near future and long-term future. And finally, some Q&A. So, what's mojo-regex? Everybody knows what's regular expression. So it's a regular expression engine in Mojo, and it's familiar to the Python RE module. So yeah, it's an hybrid. Yeah, let's talk about that in the architecture, but it's uh, an hybrid architecture, hybrid engine with SIMD optimization for performance. And the disclaimer is that it's an early stage of development, so please don't consider this production ready yet. So this is how we can use the library right now. So it's very similar to Python, except for the match first usage. In Python, it's just match. But unfortunately, in Mojo, match is a reserved keyword. I think Greek were talking about to put like a soft keyword instead of a hard keyword, but it's not done yet. So for now, we need to use match first. And yeah, so we have implemented a lot of different patterns like basic and quantifier, answer, etc., groups, alternation, but we have in progress much more, right? Like capturing group or yeah, replacement, etc. Right? Yeah. Why I build this at Smith.ai? My company, we needed to implement a phone number parsing because our company is about AI phone calls, and the phone number is very important in this kind of business, right? So there was a Python phone number, and we tried to start introducing Mojo in the code base by starting with this phone number parsing. But it's turned out that the regular expression was used everywhere in the library because parsing and formatting numbers means to uh, look for the country code, and then for each country we have a bunch of regular expressions we have to start parsing, matching, and yeah, if it is matches, the number is correct. If not, right. So it turned out that by building the phone numbers, we needed the regular expression module. There was a starting commit, but it was reverted in the Mojo community, but I realized that this was not complete. So instead of importing the Python module from Mojo, we did it the hard mode. Like I started the registration engine from scratch. But thanks to the AI coding environment we already have, agents, etc., the entry barrier was so much lower because we had a regular expression expert just in your computer, because everywhere there is a regular expression library implemented in every language you can imagine. So it is well trained for this kind of things. So I was learning thanks to the AI agents, and I was building the library. So let's talk about the architecture. This is the usual architecture is Lexing, this splitting the pattern into tokens, then passing the tokens into an AST tree, and then the optimizer is like the brain that who decides what kind of strategy we are going to use for that specific patterns. There is two different strategies, the DFA and NFA. One is faster but less powerful, and the other one is slower and more powerful. So this is kind of how the lecture is splitting the pattern into tokens. Then there is an AST node that is when you parse this list of tokens and you have a tree. And then finally, you optimize the tree with the pattern analyzer who analyze this tree and say, okay, what kind of tree we have? And it's recursive, and they decide, okay, it is simple, go to the simple engine, or it's complex, go to the complex engine, right? And all the matcher, the engines are like that. This is the determinist finite automata matcher, which is the easiest and fast one, but it's the same signature, right? So the NFA would be the equivalent, right? So yeah, dipping into the engines, the DFA is order ON, and the NFA is unfortunately order N times M, being the high stack length and the pattern length multiplied, right? Because we have backtracking, it's like a graph, right? Yeah, so the solution was, okay, let's analyze the pattern and decide it is simple, go to the DFA, which is ON. If not, the slow one, right? Yeah, let's talk about performance optimizations. We have, I have done. Yeah, the spoiler is that this is much more complicated than I expected when I started the project, but way more complicated. Like libraries are usually years long. It's a multi-year project building a library like that. I never thought about that because I was like a consumer, like many of you, but not a developer of a regular expression engine, right? So I'm still not an expert. I'm just learning. So that's one reason. Skill issue would be the first reason that is not performing well yet. So another reason is benchmarking is hard. Let's talk about that in future slides. But yeah, it's tricky, very tricky. And actually, depending on the patterns you choose to measure, it could be a final average very different by using different measurements. So it's always biased. So performance journey, and in the specific module development, uh, I find that it was hard to trace copies and allocation because, of course, we have some tricks. Thanks to Remy for this trick, the call location, which is used in the standard library a lot. But it's not easy when you are measuring third-party structs like list, string, which is in the standard library. So it's not something you quickly put in your code because it's not your code, actually, right? Yeah, the other caveat is AI generated code. AI is fantastic for generating a boilerplate like millions, many algorithms I was not aware about, and it was like, okay, please implement this algorithm, and the AI would know perfectly how to implement the algorithm. But when building Mojo code is usually works like it was Python code, so it doesn't care about pointers, no copies, etc., etc., etc. And Mojo, we can care about that, and it's just okay. There is a bunch of new code I have to review. I have to optimize this back and forth workflow. But yeah, this. But at the end, you get well if you work hard, you start optimizing everything. Yeah, and I found hard the origins, especially with recursive struct, because the AST is a node, and the node reference the children's, which are a list of more nodes. So it's difficult if you want to, okay, first not using unsafe pointers, but at the same time being able to be fast and avoid copies is a difficult balance. Maybe is you cannot avoid that, or maybe it's something we can improve in Mojo, or maybe in Mojo compiler, maybe the standard library. Yeah. So compared with Rust, we are not very well in the comparison. We usually are like 100 times lower. The Rust crate is like amazing and is very well optimized, like for almost 10 years of optimization. So it's very hard to compete. And actually, there is precompile regexes and also with a lot of prefilter, a lot of bypassing some cases. So it's also zero copy. Mojo version is not yet zero copy. It aims for that, but it's not achieved, right? And also, Rust implementation claims to use DFA, which is ON for all the inputs, and Mojo is still used for some cases the ON square or N plus M order, right? Which is much slower, right? And we compare with Python, we have cases in which we are faster, but it is surprising for many of you that in some we are Python is way faster than the Mojo implementation. I can remember a talk from Chris saying, okay, if your code is slower than Python, you are doing something very wrong. And it turns out that in this case, we are not competing with Python. We are competing with old 25-year-old C library, which very low level things like go to here, go to there. So it's not a fair comparison. It's not Python actually. It's just C. So it turned out that it's fast. Of course, the code that use the regular expression library could be much slower, but we are comparing just the library itself. So yeah. So, and actually it's compiled with pattern compile in a very smart way. So yeah, this is, it's not easy to beat Python in this case, right? Yeah, the benchmark setup was, okay, I use the bench module for benchmarking in Mojo, but when it is for when it's about comparison with Python Rust, I had to implement a lot of code for mimicking the bench library, and then output JSON and compare results, right? So there was like a table like, okay, this is the column of Python, Mojo, speed up, etc., right? Yeah, but I have told at the beginning of the talk that benchmarking is tricky, is hard. And today I just realized that there are something off in the previous comparison I am using for like have a reference of how fast is the library. For example, if you compare, this is with Python and this is with Rust, the the wildcard pattern, which is okay, always there is a match with this pattern. I bypass this pattern to just at the beginning of the engine say, okay, let's return true. And it turned out that when I measured this with Python, was still like 30 times slower than Python and maybe 100 times lower than Rust or more. But then it was say, okay, this is not possible. So let's build a specific script for that specific case. And it turned out that it's actually faster when it's precompiled than this is Mojo. This is much faster than Python, and actually it is faster than Rust. So there is something odd in my benchmarking setup or the bench library. I don't know if it's about global variables that are wiped out in each iteration in the Mojo thing. So it's unfair comparing it with Rust or Python. I don't know what's the reason. Maybe some of the smart guys here could have a reason for that, but I will investigate this is much more because it was today when I found, so I hadn't time to deep into. So let's talk about some of the optimization done. One is try to avoid copies everywhere. For example, this is the naive implementation, but I finally have a very fast, way faster implementation, which is using unsafe pointers and then the children length, and then in the nodes, just the index with SIMD with all the indexes up to 255 children that we can store, and the pointer to the register. So we have the pattern like the string here in the register. It's not in the slide because it's a simpler version. Of course, it's not a complicated code in the library, but we have access to the pattern, the string, and with no copies here, right? So yeah, more optimizations. Yeah, classifying the pattern. I was talking about that before. Like if it's simple pattern like literal or simple quantify, we can do it with DFA, but this has alternation. So you need backtracking. So if one path is not going well, you have to go back and try this second path. So you need NFA. I don't know how Rust implement this because it claims that it's using DFA always. I have to take a deeper look. How can we possible? Yeah, but it's work in progress. So the SIMD, of course, Mojo is awesome for handling SIMD, like it's built in out of the box. So instead of using one chart at a time to compare all the charts into a pattern, we can have a lookup table and yeah, and use the dynamic shuffle. Thanks, Seth, for this trick. Yeah, this is awesome. You can theoretically you can have 32 plus speed up, right? But then there is an overhead. Sometimes I have to roll back some optimization because it was 3-4 characters, so it was not worth it using SIMD for that single cases. Of course, memory optimization, try not to allocate something in the heap, but in the stack, of course. And yeah, using global, I know that the global variable support in Mojo is not complete, but there are some workarounds thanks to Chris that point me in the right direction. So I just use this kind of cache, a global variable cache. So I just need to build once and not in every node. Yeah. So of course, the another great feature in the Mojo is the meta programming. So using compile time optimization, like this kind of aliases, and you always will have this already calculated in the binary. So yeah, this is going to it's a micro optimization, but everything counts, right? Yeah. So the roadmap for the future would be first more SIMD optimization. I think we are going to I am going to follow the set advices suggestion to be like use SIMD wherever is possible. Yeah, I'm working actually in compile time pattern optimization, like improve the compile, like try to denormalize everything. So when it's compiled, we have a lot of information in the compiled areas, which is also cached. So yeah, And of course, futures. Future is the remaining patterns we need to implement, like, yeah, and non-greedy quantifiers, name capture groups, match replacement, and of course, Unicode support. We are using now bytes, but it should be using Unicode. And in long term, yeah, there is a lot of stuff we can build, especially the GPU acceleration is something I'm not sure. I'm not an expert. I have to investigate a little bit more. I found some papers about that, but my question is, I'm wondering is it's worth it doing when not all the servers has GPU, and we are not talking about AI, we are talking about just parsing text. So I'm not sure if it's worth it doing it, but yeah, I will take a look. Yeah, this is the resources, the way to add the package in your code and just using it. Yeah, there is a lot of unit tests and like hundreds of unit tests. It's not production really in terms of probably performance yet, at least if you want to be state of the art. But I think it's pretty stable in terms of yeah, like matching the right things, right? So thank you. Feel free to contribute, report usage, or just giving me guidance because again, I'm far from being an expert in this thing. So I would thank any advice, any guidance, and I will try to implement it. Yeah. Questions?
Awesome. Thank you so much. That was great. There are a couple of questions in the chat. I think the first one is from Owen. Would you consider a mode where DFA is the only option? The reason the base Rust regex crate is DFA only is partially due to regex denial of service attacks. In some cases, the regex is user controlled, and as a result, guaranteed linear time evaluation is a valuable security property.
Yeah, I will consider it. Again, Owen is a very good example of an expert that can give me great advices. So I wasn't aware of the denial of service attack in Regis, so I will try to read the documentation and yeah, thank you.
I think the next I think Owen has a second question. Do you have any thoughts on whether having a compile time known character set would be helpful for optimization? For example, ASCII, Latin 1, UTF-8, etc. And then I don't know, I think this is part of the question for GPUs. I think that could be useful in an ML pipeline if you want to use regex to search for forbidden patterns in a heavily batched environment.
Oh, yeah, about the first question, I think I was taking a look at the Rust code, and it was had like low level tier and high level. The high level is aware about the UTF-8, etc., but the low level one was caring only about bytes. So my approach would be more or less the same, following I think the Rust author, the Rust release crate author is it's amazing, and actually they built their the benchmark many of the languages used for comparing the library. So I think I will follow the Rust code for the future. So I think yeah, it's great. And the GPU, yeah, it could be useful for GPU too. But my point is, let's use 100% of the SIMD first, and which is available in all the computers in the world, or no, most of the computers in the world, and then we can jump up to GPU. Yeah,
Any
about the Python naming is I don't know where is used the non-snake case naming in especially the regis the regular expression library. But yes, I would not follow if it's Java based naming conventions. If like it was an error in Python, like the login library, so I will not follow that. I will stick with the snake. Yeah,
awesome. Thank you so much again. This was really great.
thank
I'm
you.
over to Amir, who's going to give us an update on Apple GPU support.
Hello, everyone. My name is Amir. I'm an intern here at Modular. I'll be presenting about a very exciting project I've been working on throughout summer, which is basically enabling Mojo on Apple GPUs. Uh, for for this slide, for this presentation, I'll go a little bit about the project overview. I'll talk a little bit about some of the challenges I faced and some of the implementation designs without going very technical on that. And then at the end, I'll show like a small demo and answer some questions. So a little bit about the project overview. So the project is all about enabling heterogeneous compute and local GPU development for Mojo developers. This is like the modular vision. And we all know like Mojo is already like supported on both NVIDIA and AMD GPUs. And what we want is basically to add another GPU vendor, which is Apple GPUs here. And this is just one step towards more heterogeneous compute. And what this enables is another like very nice bonus, which is for AI developers that work on their MacBooks. It gives us because of the stack, because of the how Modular implements all the stack, how Max is built on top of Mojo, we can basically run local models on laptops basically. And I'll give an example why this is important, especially for Apple devices. Usually a Llama model, a Llama 3B model, which is like FP16, it takes like around 18.5 gigabytes of memory. And typical like non-Apple GPUs have like between 6 and 16 gigabytes of VRAM. There are some very high expensive ones, but the typical ones are between 6 and 16 gigabytes. But Apple has this unified memory where it allows up to like, because of the GPU and CPU sharing the memory, it allows up to like 36 gigabytes of memory. So this is like, it would enable us to be able to run a Llama model 3B, Llama 3 8B model with FP16 without the quantization much, and be able to run it on a Apple GPU. So this is nice. We want this. So how can we get this? And it's not just we want to be able to run Llama, we want to run fast. But this is like a very big goal. I'll dissect it into three like small bricks or milestones, which is the first one, which is being able to run a simple kernel, a hello world example on an Apple GPU. From that, we can build a bunch of kernels and then be able to run Llama. And finally, we'll be able to optimize Llama. And in this presentation, I'll mostly focus on the first milestone. This is what I worked on. This is what we've already achieved. So yeah. So what's a hello world example on GPU? A hello world example is simply a vector add. You take two vectors, you add them, you put them in a third vector. It's pretty simple, but this is like the hello world for GPU programming. Uh, to go from this code, how does this code go into execution? I'll give some background, some components to explain, basically give some background for what I'm presenting and the stuff that I've worked on. So I'll talk about how we take from code and we compile and then we go into execution. So the first thing is we have some code usually. We have some compilation like some Mojo code We import from the standard library, we write our main function, we write our kernels, and then we do something like mojo build. When mojo build, what mojo build does is it goes into our own compiler, which is we call keygen. I think there's a public tech talk about that. If you want, you can refer to that. But then from keygen, we lower to LLVM, and then LLVM outputs a bunch of binaries. One binary for CPU, one binary for GPU usually, if you're compiling for GPUs. And then after that, we have a runtime engine. This is, I'll call it async RT, so this is like the engine that handles the basically execution and collaboration with the device driver. If we take that runtime, we add to it the binary, we'll be able to basically run Mojo on a GPU. So what are some of the challenges for this project? First, it's a big project. It involves multiple modifications across different components. So all those components that I mentioned, those need to be changed, and like they have to interact perfectly with each other. The second thing, which is vendor independent programmability, and this it's easier to explain this using a piece of code. Going back to our vector add, which is in Mojo, we write it like this. We take two inputs and an output. We get the global index, and then we do some arithmetic. And if we were to go into CUDA and to do on NVIDIA GPUs, we'll do something similar. There's some annotations, but the concept is still the same. We get the thread index, and then we do some arithmetic. Same thing for AMD, and a little bit similar on Apple. So on Apple, we usually use metal shading language, which has a little bit more differences. And if you notice the code for MSL, there are some more differences, which the first one being argument annotations. So here you see we have to add like buffer at 0 to indicate the argument place. And then there's this very different than CUDA and OpenCL, where we have to pass the thread index as part of the arguments to the function, and not as it's not a global variable like what we do in CUDA and OpenCL. So this is like a different shift in paradigm, but what we want is for Mojo to be able to encapsulate all of those three, and I'll talk a little bit later on how we handle this. There are two more challenges. Mostly, the challenges are Apple is closed sourced, so we don't have LLVM backends upstream, so we'll have to handle that our own. And the other one, which is Apple uses LLVM. We know that it uses LLVM, but it uses an old version of LLVM, which gives us more complications that I'll talk about later. So a little bit about the design. Going back to the components that I talked about, we have these similar components. I'll do some modifications on all of those. But one thing is, because of the lack of LLVM backend for Apple, what we do is we take the LLVM code, we generate a bytecode that is similar to what Apple would expect. Apple has their .r bytecode, and then we basically generate that from LLVM, use Apple to create this as a metal library, and use that metal library with our runtime. This is like an overview, the steps of each component, what needs to be done, and stuff like that. So in standard library, I'll have to include like GPU info, and like some of the functions that I have to include, Apple-specific functions. In Keygen, our compiler, there are some ways we need to create a target machine. And LLVM, I need to do some modifications to the LLVM to make it output something that Apple would expect. But there's also another thing which is requires a custom bitcode writer. I'll talk why do we need this, and then a little bit implement the device context for Metal in the runtime. So for standard library, I think it's a little bit simpler. So here we have like in host.info, I think. So we have like the GPU info. This is just a declaration of the Apple GPU host info with some of the information about the Apple info. And we can see like the target is going to be Air64-Apple-macOS X. This is what Apple expects the triplet to be. This is not an LLVM triplet, so we have to be careful about how we handle this. And some functions like has Apple GPU accelerator and whatnot. Another thing is intrinsics. So usually for example, for thread index, we have defined LLVM intrinsics, like NVIDIA has LLVM.nvvm.read.something. Those are intrinsics that are specific to the hardware. And what we want is to try to encapsulate some of what Apple would expect. However, those are not LLVM intrinsics. So, but we mask them as LLVM intrinsics, and then we handle them at a later stage. This is an example here for when it's Apple GPU. On the for LLVM, it's a little bit hard. This is like big bunch of what the project I had to work on, which is working with the LLVM. If we take an example, we usually write a .metal, which in MSL it's .metal. We use the xcrun metal, the compiler, to compile. It compiles to something called .air, which if we can see here, it has the LLVM magic number, so we know it's an LLVM bytecode. So we try to disassemble it and we get something like this. I'll show this here. I'll focus on a little bit of parts of this code. There's a lot of information here, but the main idea is if we look at the triple, for example, we find out like Apple requires Air64 Apple macOS. So that's one thing. Another thing is this kernel metadata. So there's a lot of metadata that Apple require. One of them being air.kernel, which is the entry point for the kernel. It expects the function signature, the pointer to the function, and then the outputs inputs. And the other thing is we check the arguments. So here the arguments are become part of the metadata. And everything previously we had like buffer at 0 or thread index. Those became more became metadata for in the LLVM. So we have to basically do something to do an LLVM transformation, transform like an LLVM to LLVM pass, which takes the LLVM and basically tailors it into something that Apple would expect. But this doesn't solve the problem because we still have this issue of extra argument here, basically, where Apple expects the thread index to be part of the argument, and also we have those buffer annotations. So for buffer annotations, it's simple. We take the arguments in order. First one is buffer 0, buffer 1, and buffer 2. But what happens for this thread index, thread position and grid, basically? So to handle it, we let the compiler do it. This is not something that a Mojo user should do or focus on. We wanted to like remove all the complexity. The compiler is going to do it, and I'm going to reveal the like secret for this magic. It's basically every time we compile a function, what we're going to do is we're going to insert those 3 arguments that Apple expects. Those are like 3 uint arguments basically for .x, .y, .z. So those are going to represent thread index, block index, and block dim. and we add them at the end of the function, and that let the compiler basically replace all the intrinsics that required those calls with the with the respective argument. So that's simple, but yeah. Another thing I mentioned is requiring a bitcode writer. I'll say, why do we need this? First, I'm not sure how everyone is familiar with this, but in LLVM, before LLVM 15, there was something called type pointers, which was basically each pointer had the type information in it. But then in later versions in LLVM 15, we had opaque pointers, which is basically a pointer is just a pointer, and everyone that accesses the pointer knows the type of the pointer. So we don't have to include the type information. And the issue here is that it seems like Apple uses type pointers. If you use opaque pointers, it doesn't work. It seems that Apple is basically using type pointers, so we need to be able to generate type pointers. And the issue is LLVM totally removed type pointers. So we have to create our own bitcode writer to basically emit those type pointers. And to do this, there's like two solutions for this, two steps for this. First thing is we need a pass which basically does a type inference. And to do this, we do something like we insert no-op casts. This is something that DirectX does because they also require type pointers. So we add like no-op casts, and then we have the bitcode writer, which basically generates compatible code for Apple. And finally, we have the metal device context. It's just the device context, but for Apple. This is basically the implementation for enqueue create buffer, enqueue copy, or enqueue function. And for this, we use Apple's Metal CPP API. So Apple has this Metal CPP API, which is open source, and then we basically can use it to interact with the GPU, and we do that. If you're familiar a little bit with how Apple executes a command on GPUs, you usually have this command queue, which is equivalent to a stream. You also have like command buffers, and you have to encode buffers and then commit the buffers into the command queue and do all those stuff. This is all handled by the execution engine, async So yeah, like this is some sample details of enqueue create buffer and enqueue create host, but yeah. I think the uh, best part now is showing you a demo. If anyone has questions now, feel free to ask the questions. I can switch to here.
Amir, there was one question in the chat, which was, at which stage of compilation is this insertion magic happening? Is it at parsing, generating IR, or later?
So this is after parsing. This is before generating IR. No, actually, after we generate. So this is at the LLVM stage. Before emitting the bitcode, we and for so basically we do it before we do LLVM optimizations. We skip the LLVM optimizations for Apple for now, and we just do that pass and do the insertions, and then do the bitcode generation. So it's basically at the LLVM level. Does that answer the question? I hope it does. So yeah, I'll show an example. This is like, I hope you can see my screen here. So this is like a simple example, the vector add example, which basically here I'm using a device context. Is it visible, or should I maybe I do it like this?
Yeah, that's helpful.
Okay. So yeah, so we have a device context here. This is going to create the Apple device context. This is just to verify that we're using Apple. So I'm calling this. And here I'm creating three buffers, three device buffers here, LHS, RHS, and output buffer. Those are just buffers. For the first buffer, I just fill it with 1.25. And for the other one, I want to give it some random numbers, not fully random, but so I created a host buffer and filled this host buffer with this formula, 1 plus something in terms of I. And then did enqueue copy, which we know enqueue copy takes from destination host. So we're copying from host to device. And then I'm basically launching a kernel here. This is the grid dimensions. I'm providing this enqueue function. And then finally, I'm outputting this. This is the vector add example. So here I'm using thread index dot. I actually can use global index.x also works here. So if you do global index.x, this also works. And then we're just checking if less than size, we are just doing the addition. And so yeah, now we run this example. Okay, this is some debug info I inserted so that we can see I'm using the M3 Pro chip. And then, yes, we can see here has Apple accelerator is true, and then we can see that the kernel execution is successful. Yeah, that's for demo. Yeah. And next steps, so now we've basically achieved being able to write kernels and execute them on Apple. The next step is basically do more complex and test more complex kernels, including like more complex structs like layout tensor and other kind of matrix multiplication or something. And then from that, we should be able to run Llama once we have the sufficient Llama like kernels. After we have the naive implementation for Llama, we'll do some benchmarking, and then at the end we can optimize for Llama for Apple. And yeah, so this is my slides, my presentation. This is I talked about this is about basically running Mojo on Apple GPUs. I talked about some of the challenges and basically some of the future directions. Thank you. Questions? I'm happy to answer any questions.
Amazing. Thank you so much, Amir. There is one question in the chat. Enabling such optimizations from LLVM may be quite tricky, right? If Apple does not provide open source for LLVM, with this magic, we are operating on custom IR, which LLVM does not support out of the box, question mark.
So yes, the optimizations for LLVM are a little bit tricky. For now, we don't use them. Maybe we can do some stuff that are like hardware agnostic, but there might be some issues with, like, it could enable some instructions that we don't need. If Apple do not provide with this magic, we are operating on a custom IR which LLVM do not support out of the box. Basically, yes. We're basically at the last stage. We use this LLVM to emit LLVM. It's still LLVM bitcode, so we can parse it. However, it's LLVM bitcode which is compatible with LLVM 14, mostly compatible with LLVM 14, and with extra metadata. It's still LLVM, so however, it has more data that Apple requires. That's the only thing that differs. So I can show like an example of the IR, but we can still like disassemble it, and it's still LLVM bitcode.
Thank you again. That was a great presentation. We're going to open up for more general Q&A. There are a couple of questions that were submitted ahead of time. So first question, what's the next big thing coming to Mojo as a language feature?
I want to ask a question about the question. What is how you define a big thing, right? Like what do you want to know?
Yeah, is the person who submitted this here? They submitted it via Google Form, so not
Okay.
100%
But
sure.
if the person who submitted it are in the meeting, please like speak up what you want to know, right? Because I can give you one sentence answer, but I think you want more, right?
Yeah, why don't you just give your answer, and if they can clarify, they'll probably chime in.
Yeah, I can say that we're still in that stage. We are bringing up the language to be as expressive as the GPU programmers want it to be. So parametric traits, as in the comments, we're thinking about it. There are some difficulties, some conceptual difficulties, but we'll add the required keyword first. We will add struct extensions. They're already on the plan. The default method implementations and traits are also in the works. But it's all like small features, right? From your standpoint, I think you're asking for like, what's a big juicy thing coming, right? So
I would challenge that. Requires is not small, and it will be
I
super
know,
useful in the library. But
and it's really big, and I think that it's underspecified. It's not clear. We might need to make that feature very potent, very powerful in order to be helpful. So it might be quite a journey, right? But all these features are basically it's a way to encode constraints into the language, right? So I think that's where we stand. We want to make the parametric polymorphism in the language more powerful. After that, I don't know, classes, existentials, not this year, right? So let's work with the parameter space first. I'm just watching at Joe's picture, see if he nods or if he wants something else, because his team is our first client, the most important customer, right?
it just depends on what timeline horizon you're talking about. 2025, or are you talking 2026 already?
Thank you. Next question, is support for web GPU planned for the near future? And the same for WASM from Isaac.
Again, the way the question is framed, is it planned for the near future? No. Right? If we define near future the next 3 months, we're very unlikely to do web GPU support in that time frame. Would we like to add web GPU support in the future? Yes, definitely. So again, what should be the priority? Should be web GPU support or SPIR-V support first or some other target? That's going to be a very great debate, right?
Thank you.
If somebody in the meeting knows how Chapel did the vendor agnostic GPU support and can talk about that, that would be great because we can learn from the mistakes of the others, right?
Mhm. I think we have one more question. It will be really interesting if there will be some way how to call Mojo from Rust or Zig the same way as calling Mojo from Python. Why? Because the support of GPU programming in Rust and Zig are really bad compared to Mojo. With this, Rust and Zig programmers can use Mojo for GPU programming, and with time, maybe they migrate completely their CPU code to Mojo when they see the performance that Mojo can bring. And this is also from Isaac.
Evan, are you in the meeting? You had some thoughts about how to make Rust Mojo interop work, right?
Yeah, I could talk a bit about that. So there's kind of two sides to this problem, how to make Rust and Zig call into Mojo, and then there's also vice versa, how to make Mojo call into these other languages. Um, the latter one is harder and also not what they're asking, but I'll talk about the former. This should be possible, and it should even be possible to work with generics. I proved that something like that is possible when I was working on Veil. It is in theory possible. Someone else in the comments mentioned an interesting uh, factor, which is that this might encourage language or programs that have two languages, which might add to the problems rather than solving problems. Um, but in theory, it should be possible. I don't see any particular reason why it wouldn't be possible. It would just be really hard to pull off because like then you have multiple language programs and that's always kind of a headache. Any follow-up questions or does that mostly answer it?
I think Todd asked that, okay, can you guys just do it through C bindings? But yes, we can do that, but that's not what people want, right? People want like avoiding the C bindings. Like the languages talk to each other directly.
Yeah, doing C bindings makes sense for Mojo to Zig, uh, and kind of Zig to Mojo. Be really unfortunate if we had to go through C bindings for Rust Mojo interop because like there's unsafe concerns all over the place. You can't really check things as well as you could in theory. And also C bindings are just really annoying in general. Like they're hard. You often have to resort to auto-generating bindings, and that imposes constraints on both the Rust side and the Mojo side. And it gets rid of a lot of the architectural benefits of, well, the safety benefits of both languages. Yeah, it's a big topic. I could talk for hours on this, but we're at time, so I'll let you go. Yeah.
Thank you, Evan. Any other last questions for the team before we wrap? Do you plan to land linear types within 2026? That might be an Evan question.
Yeah. I mean, hopefully sooner. We got how many more months? Like 4 or 5 more months. Hopefully we can land linear types fully before then. We have linear types today. It's just that they don't work with conditional conformance. So you can't, for example, have an optional of a linear type. Conditional conformance is the hard part. I don't know how long conditional conformance is going to take, but once we land that, linear types are complete. Yeah.
Awesome. Thank you so much. A huge thank you to everyone who presented today and everyone who came, attended, asked questions, and we will see you next month.